Alright, 19th go is a charm. G'day folks, welcome to another tutorial. So today we're going to be looking at a couple of things. First of all, we'll look at some SSE arithmetic instructions, and then we'll finish up by looking at some dynamic memory allocation in assembly. So first of all, SSE arithmetic instructions. All of these are for floating point. If you want to do integer arithmetic with SSE, you use the MMX instructions and SSE registers. But these are all for floating point. So we'll just look at some basic ones today. We've got addition, subtraction, multiplication, division, square root, max, and min. And you pretty much make the naming of the mnemonics is pretty simple, really. We put whatever instruction we want to do, so add, for example, and you follow this by P for packed. Or if you want to do scalar, you put an S there, and then you follow that with the data size, so S for singles or D for doubles. The packed here means SIMD style, all of the operations at once, so you could be doing an operation on, say, 4 singles or 4 32-bit floats, or you might be doing a packed operation on 2 64-bit floats. And the S just here is scalar. That means don't do it SIMD style, just use the bottom-most element from the registers. So if you do, say, addition and you're using scalar, then the top elements of the registers are unaffected and only the bottom registers are actually added together. Alright, I want to mention also that the single floating point instructions are from SSE 1, and all of the double ones, or the 64-bit doubles instructions, are from SSE 2. Alright, here's a few examples of how to make these instructions. So here we've got ADDPS, which means add packed singles, and that's going to add 4 packed singles together at once, SIMD style. We've got SUBPD, which is subtract scalar double. So the S just here means scalar, the D just means double, and that's just going to do one operation, a subtraction of the low elements in the registers that you give it. We'll have an example in a minute to make it a bit more clear. The next one is mul.ss, which is the mnemonic for multiply scalar single. Or we could do min.pd, which would give us the minimum of packed doubles from SSE 2. Okay, just a few examples of the mnemonics. All of these instructions take 2 operands. The first is an SSE register, and the second is an SSE register or memory. So if you're doing packed operations, the memory operand here has to be 128 bits wide, same size as an SSE register. Or if you're doing scalar operations, then the memory operand has to match whatever data size you're working with. So if you're working with a single or 32-bit float, then it's got to be a 32-bit memory operand. Or you might be using a 64-bit memory operand and working on doubles. Good stuff. Alrighty, so an example of add packed singles. Here we've got the mnemonic ADDPS, and for these examples I'm just using 2 SSE registers. Remember, the second one here could be a memory operand, but I'm just using 2 SSE registers, and it's XMMO and XMM1 in these examples. As per usual, we've got the destination is the first operand, XMMO in this example, and the source is XMM1. And it's pretty easy really what these do, since we've looked at other SIMD instruction sets. All that happens is the corresponding elements of the 2 registers, XMMO and XMM1, are added together, and the result is stored in the corresponding element of XMMO, our destination operand in this example. So 5.2, the first element of XMMO, will be added to the first element of XMM1, which is 3.1, and we'll come up with the answer 8.3. Next we'll get negative 6.3 plus 92.1, and that'll be stored as 85.8, just add the 2 together, and 7.9 plus negative 19.2 gives us negative 11.3, and 4.1 plus 12.6 gives us 16.7. So really easy actually, just 4 operations on packed single floating point values at once because of the PS here. Okay, here's an example of subtract packed doubles. So there's only 2 packed doubles per SSE register. So whereas in the previous example we were doing 4 operations at once, if you're working on packed doubles you can only do 2 operations at once. This is pretty easy as well, but it does matter which order you put the operands in. In the previous example, if you add 2 numbers together, it doesn't matter which one you add, but for subtraction it does matter. So what happens is that the elements in XMM1 here, our source, will be subtracted from the elements in XMMO, not the other way around. Alright, it's pretty easy. Negative 6.3 minus 92.1 gives us negative 98.4 in the answer. 4.1 minus 12.6 gives us negative 8.5 in the answer. So that's subtraction of packed doubles. If we had as our mnemonic sub SD, subtract scalar doubles, then the top element would be ignored. The 4.1 just here would stay exactly the same, and the 12.6 wouldn't even be read by the CPU. All that would happen is negative 6.3 minus 92.1 would be placed in the lowest element of XMMO. So scalar is only work with the lowest element. Good stuff. Okay, these are really cool. Minimum and maximum. There's no equivalent to this in regular x86, so this is quite cool. This is all brand new instructions for SSE. Alrighty, so it takes 2 operands as per usual. I've used XMMO and XMM1 as my example, and all that happens is each corresponding element from the 2 registers is compared together, and the minimum, since we're asking for min here, is placed into the answer in XMMO. So 5.2 and 3.1, what's the minimum? The CPU is going to ask. It's going to figure out that 3.1 is the smallest of those 2, so it's going to put that in the answer, right there. Then it's going to move on to the next, negative 6.3 and 92.1. Obviously the minimum of those 2 elements from XMMO and XMM1 is negative 6.3, so that goes into the final answer. Likewise, we move on, we get 7.9 and negative 19.2, the smallest is negative 19.2. And 4.1 and 12.6, well, the smallest is 4.1. Alrighty, so if you were looking for the maximum of these 2 values, you could easily just change this to max PS. Find the maximum of packed singles, and the elements in XMMO will be the maximum of each pair of elements. Fair enough. Very cool. Or you could do, of course, min SS for find the minimum of scalar singles, and it'd only work with this lowest single. Okay, moving right along, we've got square root of packed doubles in this next example. Now this one's interesting because the other examples that we looked at were binary operations. You think about the addition or the subtraction operator. They take 2 operands, so you say 5 plus 4 or 7 minus 3. But square root only takes 1 operand. You find the square root of 100, or you find the square root of 23. So it's a unary operator, and they decided that what would happen is the values in the first operand, XMMO in this example, are completely ignored. And what you actually get is the square root of the elements in the second operand. So XMM1 in this example. And I just chose these numbers randomly. All of these numbers are random pretty much. So what we're going to get if we say square root of packed doubles XMMO, XMM1 with these values here in XMM1, we're going to get the square root of 92.1 in the lowest element, which gives us about 9.5969, etc, etc, etc. Just dot 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 after that. And we're also going to get the square root of 12.6. So it finds 2 square roots at once. It's very quick. Really good way to do it. 3.54 is what we'll get there. So the first operand is pretty much completely ignored. Alrighty, so just something to be careful of is if any of these have negative numbers in them, if your elements in XMM1 or your source operand, whatever you happen to be using, has a negative number, you'll get indeterminate as the answer, since it's not defined. It doesn't do complex maths, just regular floating point arithmetic, so you'll get negative 1 dot pound ind. Rather strange answer. Also, yeah, obviously you can use the same register as both operands. So if this first register here happened to be XMM1 as well, all that would happen is instead of 12.6 and 92.1 being placed into XMMO, we'd actually get those two answers in XMM1. So these two elements would be overwritten with the square root of whatever happens to be in them at the time. And like the others, we've got square root SD, square root, PS for packed singles. Yeah, lots of different versions. Okay, we're going to have a break. Okay, cool. Break. Alright, I forgot my pencil in the last one. Hopefully my pencil's back now. My cursor pencil. Anyway. We're going to move on now to have a bit of a look at dynamic memory allocation. We're going to start by first of all sort of asking, what is the data segment? We've been defining it in pretty much all of our programs, and what exactly is it? Well, it's a chunk of the exe file, or your executional file. So Windows loads this chunk along with the assembled code segment into RAM when your program is run, and it being a chunk of your exe file means, interestingly, that if you add 1 megabyte of data to your data segment, the resulting exe file, when compiled, will be around about 1 megabyte larger. And it's going to compile really slowly as well. Okay, so let's have a bit of a examine of exactly that. I've got here, I don't know how well this is going to come out, but I've got a little program that I've made called Data Segment Fun, and at the moment it's about 32 kilobytes big. You can see here from the size, and here's the code to it just over here. We'll go through this in a minute, but it's pretty simple really. There's nothing much happening. I just call two functions, allocate and deallocate, which we'll go through in a minute. But the point of this exercise is that there's nothing declared in the data segment at the moment except for this single quad word, and the resulting file, as we just saw, was about 32 kilobytes. So if I define a byte, maybe my byte array, db, it's a byte, 1024 by 1024, dup, a. Okay, so I've just defined a 1 megabyte array of the character A in my data segment, and if we compile that and we go over here to our little window, this is where it's actually compiling to. It's 32 kilobytes at the moment. There we go, off and running. Let's just stop it. Okay, so the result from that, the exe file has gone from 32 kilobytes to 1.2 megabytes. So we can see that adding that 1 megabyte array actually increased the exe file size bigger than 1 megabyte. It's now 1.2 megabytes big, and it started at 32, so there's some padding going on as well. But what you can pretty much see is that adding data to your data segment actually increases the exe file size. And I've got a little hex editor here, hxd, and if I drop this exe file onto the hex editor, and we have a bit of a squiz at what's going on. Okay, so here's my exe file. In the hex editor, the first thing that we see is MZ, the magic number for DOS exe files, and that just means pretty much that that's the start of the exe file. That's the little stub that runs. So if you try and run this program in MS-DOS, if you happen to have an 80s computer lying around, MS-DOS is going to come up and say, nah, you need Windows, bruss. But down here, PE, Portable Executable, this is where the actual Windows exe file starts. Anyway, we're not going into that at the moment. If we scroll down, we see lots and lots of random machine code. If we keep scrolling down, down, aha! Okay, here we go. We've got just a massive chunk of A's. A, or 41 in hex. And this is the array that we defined. So there's going to be 1024 by 1024 of these A's. 1 megabyte of A's. A little over 1 million. Good stuff. Okay, so that's how you actually find the array that we declared in our data segment. Yeah, we can see that it's part of the file. Alrighty, back to our slideshow. Okay, we can find the data segment in our exe with a hex editor. Yes, indeed we can. We just did that. We know it's the data segment and that the data is not used. What? So we can change it. Yeah, we could. If we wanted to, with the hex editor, we could have typed anything we felt like into that big array of A's there and saved the exe file, and the program would still run fine. You can't usually do this. If you change the data segment to some other compiled program, it's probably not going to work. Anyway, let's not do that. Let's just say we did. Okay, so this is no good for dynamic memory. Once compiled, the exe's data segment is fixed. Okay, it doesn't get bigger, it doesn't get smaller, it is what it is. This is really good for small amounts of static and global data, like we've been using it. But sometimes we don't know how much memory we're going to need when the program is being compiled. And sometimes it changes, you know, every time you run some programs, maybe they need more memory one time, maybe they need less. Okay, so this brings us to dynamic memory allocation. And we know in C++, to get some dynamic memory, we use the new operator. So we say blah blah this equals new, you know, whatever. And what we're really doing is we're asking Windows for some more memory on the fly. Windows looks up the heap, a portion of memory called the heap, and it makes sure there's enough memory for our request. And if there is, it gives us back a chunk of this memory, or a pointer to a chunk of this memory. And this pointer might actually point to a chunk slightly larger than we requested for padding, but it'll pretty much be the same size as whatever we want, you know, whatever memory you're requesting. So once you're done using the object, you call delete, in C++ this is of course, and Windows marks the memory as not being used, and other programs are free to use it again. Fair enough? Okay, what is the heap? We mentioned the heap on the previous slide. The heap is pretty much the memory that programs can dynamically allocate whilst they run. So your total installed RAM is being used for various things, but there's free memory. If you open up the task manager by hitting Control-Alt-Delete and go into the task manager, the heap is the free part. That's how big your heap is. Windows is pretty much in charge of the heap, and you are in charge of your stack, data, and code segment. And yeah, we did that already. It's the free part in physical memory. Okay, dynamic memory in assembly. So how do we get dynamic memory in assembly? It's pretty much exactly the same as C++. We ask Windows to give it to us. Memory management is what OSs do best, pretty much. Windows, the operating system, is very good at managing memory, so we ask Windows to give us some more memory. And we do it with two little functions. First of all, there's Malloc, which is short for memory allocate, or allocate memory. Should have been alloc, but they chose Malloc. And that returns a void star, or just a pointer, a 64-bit pointer, and it takes as an integer, that's actually an unsigned long integer I think, the amount of memory that you want in bytes. So if you want a kilobyte, you say Malloc 1024, and that's the same as asking Windows for 1 kilobyte of memory. And the other function is free, and that takes a pointer that you will return from Malloc as a single operand, and it doesn't return anything. Where are they defined? Well, yeah, they're defined in a few different places depending on whether or not you're using debug or release mode. But these little C libraries, or these basic memory operations, are defined in C libraries that are being linked to our program implicitly. So we don't really have to worry about where they're coming from. But all we've got to do at the top of our assembly file is indicate to the assembler that there's two little functions that we're using and they're defined externally. So we can do that with a little xtrn or xtern, extern, at the top of the file. Okay, a bit of a look here at Malloc, a bit closer. So Malloc takes a single operand in x64, it's a 64-bit unsigned int, and it returns a 64-bit pointer. If Windows found a big enough chunk of memory in the heap for your request, it'll return a pointer in RAX as per usual. See, so this is just a perfectly normal assembly function call, or C-style function call, and our pointer will be returned in RAX as per usual. If there wasn't enough memory to fill the request, or some other allocation error occurred, we'll get 0, or the null pointer, back in RAX. Moving on to free. Free doesn't return anything. It takes a void star, or the pointer given to us from a Malloc, and it doesn't return anything, as we said. The only operand is the pointer that previous, we said that. Don't free things unless you know they were allocated by Malloc. Yeah, good idea. Okay, so you can free pointers that were given to us from the new operator with free, but it's better to use delete. You know, if you allocate some memory in C++, you might as well delete it in C++ as well. Whereas if you Malloc some memory in assembly, then you should free it with free in assembly as well. It's up to you, but it's a good idea. Alrighty, if you don't call free, Windows will free the memory automatically when your program closes, but it's always a good idea to free the memory yourself as soon as it's convenient. Nothing more to have a good day. Yeah, good on you. Okay, so before we say have a good day and we all run away, let's have a bit of an examination of this program. Okay, so this is the assembly side. Let's get rid of the gigantic byte array that we declared first. This is the assembly side of that little program that we were just looking at. The C++ side is fairly boring. I just declared two functions, allocate and deallocate, and then called them. But the assembly side is what we're looking at. So extern malloc, and it's a procedure. This is what we put at the top to tell the assembler that there's an external function called malloc that we're going to be using. And the next one, just for a bit of fun, I used extrn without the E. And same thing pretty much, just declare that there's a procedure called free that we're going to be using, and it's not defined in this file. My data segment just consists of a single variable, which I call my memory, and that's just so that we can keep track of the pointer that malloc returns to us. Alrighty, so the first function, this is allocate, and all this does is allocates 1 kilobyte of memory. And it does it by, first of all, making some shadow space, SUBRSP, the stack pointer, 10H, which is 16. And the reason that we do that is malloc takes one operand, as we said, and the stack pointer likes to be 16-byte aligned, so we round upwards to 16 bytes. The one operand that it takes is 8 bytes long, that's RCX. And yeah, we round up to the nearest 16 bytes. Alrighty, that's for shadow space. The next thing that we do is move into RCX the amount that we want. So here I've got 1024 bytes, which is exactly 1 kilobyte. The next thing I do is call malloc, the function that we are looking at pretty much. And Windows is going to give us back either a pointer in RAX, or RAX is going to be 0. So if RAX is 0, you've got to do whatever you want to indicate to the user that they've run out of memory and they should switch off their computer and never use it again. Or RAX is going to be a pointer to some chunk of memory. And all I've done here is saved the pointer to my memory, which is the variable up here in my data segment. And then I've deallocated the shadow space. This was 10H. By adding that to RSP, and we return. So we don't do anything with the memory in this example, but all good. Okay, let's see how we go. So we'll step through. I might just put another breakpoint here so we can see what RAX is when we return. Okay, so RAX at present has C. Alright, we step through. And right on the call to malloc we are now. Let's just play through that. Okay, so RAX after the call to malloc is not 0. It's 492660 in hexadecimal, which means it's all good. We had 1 kilobyte of free memory and Windows has given it to us. Good stuff. So we could do whatever we want with that kilobyte. Let's up the ante a bit. 1024. Okay, now I'm allocating 1 megabyte of memory, which shouldn't be a problem for the computer. Let's have a look. Get out of here. Alrighty. Okay, RCX equals 1 megabyte. Good stuff. And play. Once again, 380070. So RAX is not 0. Windows managed to find 1 megabyte of free memory in this computer. That's good news. If I didn't have 1 megabyte, we'd be in trouble. Alright, let's up the ante again. Here we go. A gigabyte. 1 gigabyte of memory, please, Mr. Windows. Let's see what he reckons. Okay, yep, good. Alrighty. Yeah, it took a little second there, but no worries. I've got 1 gigabyte of free memory. And that's a pointer to the chunk that Windows chose for me. You might notice that it's actually quite quick. Before, when we added a megabyte to our data segment, the program took ages to assemble, but now Windows can give us that free gigabyte pretty easy. That's a gigabyte too. It's even bigger than a meg. Alright, that's pretty good. What about we go really crazy and we ask for 400 terabytes. Okay, this is obviously going to run out. I don't have 400 terabytes. We'll see what Windows says. Okay, move 400 terabytes into RCX. Good. 0, the null pointer. Computer says no. Alright, so that's just indicating to me there that I've got nowhere near 400 terabytes. Alright, that's good. That was a complete waste of time. Okay, we'll do this. Alrighty, so down here to our deallocate, which is the final thing that I wanted to look at. This is how you free the memory that was previously given to you from a Malloc call. Alright, we skip that bit. Alrighty, here we are at deallocate. So deallocate as well, free, the function free, which deallocate calls, takes a single parameter as well. And once again, when you're making shadow space for this single parameter, you've got to keep the stack pointer aligned to the nearest 16 bytes, rounding up. So, yeah, I've subtracted 10H, or 16 bytes, from the RSP. I think for some reason the C++ compiler always seems to use something like 40H. It subtracts way more than it needs from the stack pointer. Anyway. Okay, so the single operand that this takes, we put the first operand in RCX as per usual. The single operand that it takes is a pointer that was previously allocated from a Malloc call. And like we said before, we save that to my memory. So if we move that value into RCX, we should be right to call free. And yeah, Windows will know that we've stopped using that memory. So let's just step through. There it is, 1E2660. You can see here, this is RAX. Still set to the value from allocate, or Malloc, from before, and that value is exactly the same as what's now in RCX. Won't always be the case. Usually you'll have modified it or done something with the memory in between, but it's the same in this example. Alrighty, the next thing that we do is actually call free. There we go, so Windows has now freed that 1 kilobyte of memory, and other programs are right to use it. And finally we deallocate the shadow space by adding 16 to RSP again, and we return. Okay, so that's dynamic memory allocation in assembly. Really useful. All it comes down to pretty much is if you want memory on the fly, you ask the operating system using Malloc, and then you give it back to the operating system using free. Alrighty, well that's about it, so thank you for listening. Adios.